Hey everyone, and welcome. Today, we're going to break down one of Go's most important structural design patterns. It's a pattern that lets you build incredibly flexible, scalable systems. We're talking about the composite pattern. And let me be clear, this isn't some patch for Go not having inheritance. It is Go's powerful, and I mean really powerful, answer to it. So, to get our heads around this, picture a streaming service. You've got single videos, right? But you've also got entire seasons, which are really just collections of those videos. Now, what if your code could perform an action, say play, on both a single video and a whole season without changing a single line? That's the magic trick here. That's the core problem the composite pattern solves, making individual objects and groups of those objects look and act exactly the same. So here's our game plan for this explainer. First, we'll really dig into that problem of treating one thing the same as many. Then, we'll explore why Go's lack of inheritance is actually a massive feature, not a bug. After that, we're going to compare 3 different ways to implement this thing to find the most Go idiomatic approach. We'll then look at some amazing real-world examples, and finally, we'll wrap it all up into a new design mindset you can start using right away.
Okay, let's start with a problem that I guarantee every single developer hits at some point. The source material calls it the composition wall. And this isn't some high-level academic idea. It's a very real, very practical roadblock you'll find in almost any system you work on.
I mean, look at these examples. They're everywhere, right? Your service needs to handle one request, but what about a batch of them? Your payment system processes a single transaction, but what about a whole chain? A logger needs to write to one file, but then you need it to write to the console and a file and a network socket. In every single one of these cases, you want the code that calls these things to be exactly the same. Without this pattern, you just end up with a mess of type checks and endless if-else statements that are a nightmare to maintain.
So how does Go get us out of this mess? Well, it all starts with a very bold, very deliberate design choice. Go does not have inheritance. And I really want to stress this. It's not a missing feature. It's a whole philosophy that favors a much more flexible and robust way of building software. Let's see what that actually looks like.
On the left, you've got your classic inheritance. It creates what we call an is-a relationship. A dog is an animal. This sounds simple, but it leads to really tight coupling. You change the base animal class, and you might accidentally break the dog class, and who knows how many others down the line. But on the right, you have Go's approach, composition. This creates a has-a relationship. Your object has a certain behavior instead of being a certain type. It's way less brittle and a whole lot easier to manage and test.
Now, the secret sauce that makes this work in Go is something called struct embedding, which gives us method promotion. So when you embed one struct inside another without actually giving it a field name, that's what anonymously means, all of its methods become directly callable on the outer struct. It kind of feels like inheritance, but believe me, it is fundamentally different.
And this right here, this is the most critical point. This is the gotcha that trips up so many people when they're new to Go. Just because you embed something, it does not create a subtype relationship. A son struct that embeds a parent struct, well, it has a parent, but it is not a parent. You can't just pass a son to a function that's expecting a parent. Understanding this difference is absolutely key to thinking like a Go developer.
Okay, theory's great, but let's get practical. How do we actually build one of these composite types? The source material shows us 3 different ways to do it. And by looking at them side by side, we can really see what the idiomatic Go way is all about. So here are our 3 contenders. Approach A, using a function field, it's just clumsy and you lose all your type safety. Not great. Then you have approach B, using the struct embedding we just talked about. It's better, for sure, but it has this nasty little habit of creating runtime panics if you forget to initialize it, because you'll be calling methods on nil fields. And then there's approach C, interface embedding. This is the one. This is our winner. It's explicit, the compiler has your back with compile time safety, and it's super easy to mock for testing.
And this quote really just nails the whole Go philosophy. The interface approach is the best one because it's explicit. In Go, being clear and having explicit contracts always wins over implicit, magical behavior. You're working with behaviors defined by interfaces, not concrete types, and that is the absolute cornerstone of good Go design. All right, so we've seen how to build a simple composite. Now let's see where this pattern really flexes its muscles. The true power of this thing becomes obvious when you look at recursive structures and realize that Go's own standard library is absolutely full of it. The classic textbook example is a binary tree. So what is a tree? It's just a node that has other nodes. But here's the thing, a single leaf node by itself can also be treated as a tiny little tree.
They can both share the exact same tree interface with a traverse method. This simple idea is how massive, complex things like file systems, HTML documents, and even compilers are built. The part and the whole speak the same language. And you don't need to be building a compiler to use this stuff. It is everywhere in Go. Take io.MultiWriter. You probably use this. It takes a whole bunch of io.Writers, maybe one for the console, one for a file, one for a network connection, and it wraps them all up into a single io.Writer. You write to it just once, and your data gets sent to all of them. It's a perfect, beautiful example of a composite.
Here's another one every single Go web developer uses, http.ServeMux. What is a ServeMux? It's literally just a composite of multiple http handlers. It holds a collection of different handlers and, depending on the URL, it sends the request to the right one. The ServeMux itself is just a single big handler made up of many smaller ones.
You know, even sync wait group is basically using this pattern. Think about it. Each Go routine that you add to the group is a part. The wait group is the whole that lets you treat that collection of running Go routines as a single unit that you can wait on. See? The parts and the whole are all managed through one simple, unified interface.
So, we've covered the why and the how. Let's wrap this all up by turning these lessons into something really practical. A new mindset, a checklist you can use to start building your own systems this way.
Here's a quick checklist for your own code. First, the test signal. Can you easily swap in a mock for one of your components? If the answer's no, your design isn't flexible enough. Second, the production signal. Can you change where your logger writes from the console to a file without touching any of the code that uses the logger? And finally, the fail-fast check. Can you add a brand new component, a new leaf, without having to go back and change the code for the collection that holds it? If you can say yes to all of these, you've got a really solid design.
And that brings us to the most important takeaway of all. The composite pattern in Go isn't about building those rigid class hierarchies you see in other languages. It's about defining behavioral contracts using interfaces. It's about building systems where the individual parts and the assembled wholes are completely interchangeable. So the next time you sit down to design something, just ask yourself, can the one and the many be treated exactly the same?